Hi, I'm Morten Nielsen, and in this video I'm going to talk about how you can work with observed turbulence statistics in ShowCFD. So you click on this button and then you open an Excel file, and it's supposed to be in this format here. So here at the top line you have some identifiers, and then you have the position and the height observation. Then you have a table here which is turbulence intensity, and then the mean of all observations, and then it's sorted into sectors here, the same sectors as your wind climates, and in wind speed bins like this. So here you have the mean of the observation, and here you have the standard deviations of all the turbulence intensity. Maybe you notice that there are different values for different cells here, but when we go to the upper end, then it's all the same. And that is of course because when I did these observations, then there were no measurements, so we had to extrapolate in some way because it's needed by the models in the IC site assessment. The format of the turbulence statistics file is shared by the wind farm assessment tool, and it might be easier to simply generate it by the wind farm assessment tool. And here I have a project of our site, and I already have a mid-mass but I think I'll pretend that I want to generate the data again. So I right click here and then say load new turbulence intensity reference data, and then I want to calculate from some time series. And the time series then need to be in an Excel file. First you have the date and time, then the speed signal, mean speed in a 10 minutes periods, standard deviations of the means, and then the wind direction here. And the date time format that can look different for different natural setups, but you can make sure here that if you go format cells, and then it should be in datetime format, then it will be okay. So back in the wind farm assessment tool, then I click OK here and calculate it from time series. This is our format here, and that was our measurement positions, and then we press load data. So here I have my observations, and it's about it's plenty of years, and then we can inspect the statistics of all the scatter and the fitted mean and standard deviation, and then we press OK, and we go to this effective turbulence intensity plot here, and then there are some extrapolation options which you can adjust in various way, and there are documentation for the wind farm assessment tool which you can use to define it. You can say I don't want to include the lowest wind speeds when I do the extrapolation, and you can also say that I want a minimum count of observations in each bin before I can trust them. So anyway, then we have done the extrapolation, and then we can go here, right click again, and then export these data to file. And then we have our file for ShowCFD. So now we can load the turbulence statistics into ShowCFD by clicking on this button and then locating the file. And when we are going to apply this turbulence intensity, then we discover that we have different opportunities, both the uncorrected one and then the mean and 90% at something called effective turbulence intensity. And to explain what that is, then we will have to look in the help file here, and it's done almost the same way as in the wind farm assessment tool. So I simply just import as part of the help file from that program. And you can, if you click here on ambient turbulence models, then we can see that observed turbulence intensity, that often it has if even for the same wind speed, then you can get different turbulence intensity in different situations, mainly due to different atmospheric stability here. And it's mainly at low wind speeds. At higher wind speeds, then usually is converged to the same level here. The normal turbulence model in the IC standard, that's something which has a shape like this, and it's supposed to be compared to the 90 percentile of the scattered variation here. So that is a comparison we have to make. And if you then look at the output of a model, then it's usually just the prediction of the turbulence intensity at neutral atmospheric stability. So then, and you'll get exactly the same result if for all wind speeds, both for the flow model of WASP engineering and also with the WASP CFD. And but we have to do something to make the comparisons with IC standard, and this is why we needed the observed turbulence statistics. And in wind farm assessment tool, then we had different options. The only one implemented so far in ShowCFD is this second one here, that we say we have the reference site maybe at a mast here, and then you have some turbulence intensity here, and then you compare it with what you could observe here at this site. Or this is a model and this is observation. Then you say what is the difference here, and then when we go to the site of the application, maybe a turbine site, then we add that difference here. But we should remember that maybe there's a speed up effect from the reference site to the site of the application, and this is this beta factor here. And you both need it when you look up in the tables, and also when you because you normalize with a local wind speed, then you also need to apply it again here. The normal turbulence model of the IC standard was used for the design load cases, and they were run for different wind speeds but not for different directions. And when we make the comparisons with the site conditions and the normal turbulence model, then we should make some kind of average, and this is done in this way. This is an integral over all directions, and this is turbulence intensity, and this is the probability of wind coming from different directions at a certain wind speed. And then the average is a little special because it's you raise the turbulence intensity to this power called the Wöhler exponent, and then we do an integral and then take the root again. And the purpose is that this should be the uniform turbulence intensity, which cause approximately the same fatigue damage as varying turbulence intensity from different wind directions. So then when we look at the turbulence intensity map here, then we can actually change that for being uncorrected or showing the mean or this 90% level or the effective turbulence intensity. And for site assessment, then it's effective turbulence intensity, which is the relevant ones. And we should also make this correction with the turbulence structure correction function here, or factor. And of course you remember that that was designed by this terrain assessment, where we have selected a site here, and then we can make an analysis for fitting planes in different directions, and we do that for all sites here, and then we can map this this factor here. We can now add the mask here also for the probability distribution and for turbulence. And then you see that there are certain areas here which are constraints. Actually here the problem for turbulence intensity is probably at this site that it's a rather high wind speed, and here it's probably these lower wind speeds here. And to study exactly which wind speeds are causing the problems, then instead of selecting all these things, then we can say probability distribution just for selected local wind speed. So no problems for 15 meters per second. Then we can go down and say, oh, it's crossing here, maybe there were some problems here, so let's investigate that. And we could take the wind speed a little bit higher. So you can see that most of these sites it's just crossing here. So this is where we have the problems for the PDF. In that way, you can get a feeling of where the problems are, and maybe also use it when you are maybe discussing it in greater detail with the manufacturer.